Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is counting spaghetti. It appeared in October lunchtime and has a difficulty level of medium hard. The prerequisites for this problem are math. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the detailed solution approach for each of the subtasks, followed by which we will be seeing the pseudo code and then doing a quick go through of the C++ code. The problem statement goes as follows. Given two integers L and R, assume that you have all the integers in the range L and R inclusive of L and R. That is, assume that you have all the numbers L, L plus 1, L plus 2 up to R. So if you have all these numbers, we have to find the total number of distinct sums that we can generate from using elements from this sequence. Okay, so what do we mean by that? Let's see through a small example. So let's say L is given to us as 3 and R is, let's say, 5. So the elements that we will be having will be 3, 4 and 5, right? So what are the distinct possible sums that we can generate using these three elements? So using a single element, we can generate the sum 3, 4 and 5. Using two elements, we can generate the sum as 7, 8 and 9, and using all the elements, we can generate the sum 12. So we have to report the count. That is, we can generate 7 distinct sums over here. So we have to report the number 7 if the input was L is equals to 3, R is equals to 5. Okay. The constraints for the problem are the test cases can go up to 1000 and the numbers L and R can go up to 10 to the power 9. Although for smaller subtasks, the constraints may be special and smaller. Now, let's see the step-by-step approach to this problem. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. We start with the simplest subtask, that is subtask 1, where it is given that L is equals to 1 for all cases. So say we have n elements, that is 1 to n, then what is the distinct number of sums that you can get using single element? So we can generate the sum as 1, we can generate the sum 2 and up to n. So these are the sums that we can generate using a single element. So what is the maximum of this? We can generate n, right, using a single element. What about if we decide to use two elements? So we can take this n and we can also take this 1 and generate the sum n plus 1. So we can definitely generate n plus 1 and similarly we can generate n plus 2, n plus 3 up to n plus n minus 1, right? So this is using how many elements? This is using two elements. Using two elements, we can generate the sum n plus n minus 1. So similarly for three elements, we can generate the sum n plus n minus 1 plus 1. So I can write here n plus n minus 1 plus 1 up to the sum of last three elements, right? So this is the maximum sum that we can generate using three elements, sum of these three elements. So in similar fashion, if you continue to calculate what is the maximum sum that you can generate at the very end, that will be nothing but equal to sum of 1 plus 2 plus 3 up to n, which sums up to n into n plus 1 divided by 2. And in the process, you can notice that at each step we are incrementing our sum just by 1. So no intermediate values are missed. So For cases where L is equals to 1, we can generate all the sums starting from 1 till n into n plus 1 by 2. So the distinct number of sums or our answer is nothing but n into n plus 1 by 2 if our sequence starts at L is equals to 1 and ends at L. Going forward, if we look at a general case where L is no more 1, so the sequence would look something like this. It would start with L, then L plus 1, then L plus 2, then up to R. So now, what are the different sums that we can generate by using a single element? So let's call this range 1. So range 1 will start from L and we can generate L, L plus 1 and all the way up to R, right? So this is just by using one element. What about using two elements? So by using two elements, the smallest sum that we can generate is L plus L plus 1. So let me write over here L plus L plus 1. Then think of it in this way. Keep moving the second pointer to the right by one step. So at each step we will be increasing our sum by 1. So in the end, our second pointer would reach at the last position and the sum will be L plus R, right? So after the second pointer has reached the very end, now start moving the left pointer by one step each. So again you would be increasing the sum by 1. So in this way, what is the maximum possible sum that you can get using two elements? The maximum possible sum is R minus 1 plus R. And mind that you can generate all the in-between numbers. Why? Because we saw that in intermediate steps, we are only increasing the sum by 1. So we are not missing out any numbers. Similarly, for by using three numbers, the smallest sum that we can generate is L plus 1 plus L plus 2 and the maximum sum is again R minus 2 plus R minus 1 plus R. So I hope you guys can see a pattern in these starting numbers and the ending numbers, right? So if you want to generalize this by using X elements, that is, let's say Rx, the starting or the smallest sum that we can generate, let's call it Lx, okay, and the ending sum or the maximum possible sum that we can generate, let's call it small rx. So what are these values in terms of x? So as you can observe that Lx is just the sum of first x elements from this sequence and Rx is the sum of last x elements in this sequence. So by using sum of arithmetic progression, we get the following formula. So Lx comes out to be x by 2, 2l plus x minus 1 and Rx comes out to be x by 2, 2r minus x plus 1. So for a particular x, all elements from Lx to Rx can be attained by using sum of x elements and we have seen just now how to approach that. So using this approach, what we can do is that for all possible x, that is from x is equals to 1 to x is equals to r minus l plus 1, because that is the number of elements in the range L to R. So for all possible x, we can find the range Rx that goes from Lx to small rx. So once we have these ranges, what we can do is apply a standard line sweep algorithm or a union algorithm on these ranges so that we can find the total number of elements in the union of all these ranges. So if we do a union over all the ranges from x is equals to 1 to r minus l plus 1 and count the distinct number of elements in these ranges, so that will give us the answer. So this approach can be easily implemented, but it does not solve the whole problem. Why? Because the number of ranges can be at max r minus l plus 1, right? And our constraints say that r and l can go up to 10 to the power 9. and also we have 1000 test cases. So if we do a union for each of these ranges, then it will exceed the time given in the constraints. So this method is ideally better for subtask 2, wherein R and L ranges only up to 10 to the power 4. So it will work for subtask 2, but it will not get us or guarantee us 100 points. So for the final task for 100 points, we have to come up with some observations, optimization, and some mathematical calculations as well. So to start off, let's try and visualize how the ranges actually look. So let's say the range R1 on the number line goes from this point to this point. This is, let's say, R1. Then there's R2 over here. Then maybe R3, then somewhere over here R4. So all these ranges are present like this on our number line. Okay, so the starting points can be denoted as L1, L2, L3 and so on, right? So we know that L1, L2, L3 are nothing but sum of arithmetic progressions, right? And that too, they have a formula in X. So it is established that L1 is smaller than L2, which is in turn smaller than L3 and so on. Why? Because they are L1 is a sum of AP of one term. L2 is a sum of AP of two terms. L3 is a sum of AP of three terms, where all the terms are non-negative. So definitely they are going to be in increasing order, right? And same goes for R1, which is less than R2, which is less than R3, and so on. So same is established also for the ending points of the ranges. Okay. But one thing is evident from some examples is that the ranges might overlap with each other, right? So let's say if a range is overlapping with another range, so definitely the starting point of the second range will be smaller than the ending point of the first range, right? So let's try to establish this mathematically. So to give some names, let's call this range x and this as range x plus 1. That is, they are consecutive ranges. So they are overlapping. It is given to us, right? So what is the mathematical condition that we can formulate from this? We can say that L of x plus 1 is less than or equals to R of x. That is, the starting point of x plus 1th range is less than or equal to the ending point of xth range. So if we plug in the values in the inequality would look something like this. Okay, so if you rearrange the terms and take some common terms, you would get the following inequality. So this is an quadratic in x, as you can clearly see, and it also says that the value of this quadratic is less than or equals to 0 if the two ranges are intersecting. Okay, so depending on this inequality, there are two cases. Either this quadratic may have real roots or may not have real roots. If the quadratic does not have real roots, the graph would look something like this or this, right? But if the quadratic does have real roots, the graph would look something like this, as there will be some part for which the value of the quadratic would be less than equals to 0. But what is the importance of this quadratic having real roots or not having real roots? So if the quadratic does not have real roots, it means that for no integral value of x, this inequality was true, meaning that all the ranges R1, R2 up to R minus L plus 1, all these ranges are non-overlapping with each other. It means that they do not intersect or overlap with each other. So this is the case if there are no real roots. Okay, but what if there are real roots? So for example, the roots of the quadratic are, let's say, alpha and beta. Then for all the values of x between alpha and beta, the value of quadratic will be less than or equals to 0, meaning that the range R alpha will be overlapping with range R alpha plus 1. Similarly, R alpha plus 1 will be overlapping with R alpha plus 2 and so on until R beta. So these ranges, if visualized, would look something like this. So R alpha is over here and definitely R alpha plus 1 is overlapping with this, as you can see here. Also R alpha plus 2 will be definitely overlapping with R alpha plus 1 and so on until R beta. So if we want to calculate the total number of distinct terms from R alpha to R beta, what we can do is that directly take the ending point of the last range, that is R beta, and the starting point of the first range, that is R alpha, and we can just write, for example, R beta minus L alpha plus 1 as the total number of terms in all these ranges combined. Why? Because they are overlapping with each other. So we don't need to actually do the union of all these ranges individually. We can directly take the ending point of last range and starting point of first range and write this following formula. And that will give us the total number of distinct terms. So after the discussion that we just did, you can safely say that these ranges, you can directly say that they contribute R beta minus L alpha plus 1 to the answer. And what about the other ranges? So these ranges are actually non-overlapping. So I can write here non-overlapping, and also the ranges from R beta plus 1 to the last range are also non-overlapping. So although we have found out a way to find this directly, we still have to find a way to find the union of these non-overlapping ranges. So let's see how to do that. So according to the way that we have defined the ranges in our approach, the range Rx contains elements from Lx to small rx, right? So we can say that the number of elements in this range are Rx minus Lx plus 1, right? So we can say that. So this is just for one range. But what if we want to find the summation of elements, number of elements in a range, that is from x is equals to, let's say, some L to x is equals to R. So how will we mathematically formulate that? So we can write it as summation x is equals to L to R Rx minus Lx plus 1, right? So what will this give? This gives me the number of elements in RL, then RL plus 1 up to R small r, right? So if we plug in the values in this formula, what will we get? So we will be getting summation x is equals to L to R. Rx is nothing but x by 2, 2r minus x plus 1, and then minus 2l plus x minus 1 and a plus 1, right? So we will be getting this. So after simplifying this, factorizes 2. So now maybe you can take a pen and paper and try to derive what the formula for this summation will be. I'll be directly writing the formula now. So the formula comes out to be as follows. So yeah, this is basically the formula that you get on solving this whole summation. Okay, it is important that you do it by yourself, because if you plan to use some tricks like summation x square from, let's say, L to R, if you are planning to write it as summation x square 1 to R minus summation x square 1 to L minus 1, this won't work. Why? Because the constraints on x are so big that these individual numbers would actually overflow. So it's better that you factorize and simplify the formula yourself so that it does not overflow at any point of time. So once you have this formula, you can easily find the sum of Rx over any range of x, that is from L to R. Finally, let's say that the formula that we just saw, let's write it in a function known as range sum. Okay, so if we write a function known as range sum, which takes two queries L and R and returns the sum of ranges from x is equals to L to x is equals to R, then our final answer will be as follows. First, we will find the roots of the quadratic, that is alpha and beta, if they exist. If not, then we directly apply range sum on 1 comma r minus L plus 1, right? But if the roots do exist, what we will do is first we will find the values alpha and beta, and then our final answer will be as follows. First, we will find range sum from 1 to alpha minus 1. Then we will add R beta minus L alpha plus 1 to our answer, which is the contribution of these ranges. And then we will finally add range sum from beta plus 1 to R minus L plus 1. Okay, so that completes our final answer. So the important point in the solution was to come up with the condition for overlapping of ranges and then to simplify the formula of summation of elements in ranges by solving it mathematically. So guys, did you know that CodeChef is doing an awesome job by uploading and taking free live classes on Unacademy and YouTube? Courses like Introduction to C++, Java, Dynamic Programming, Recursion are some of the topics that are being covered in these live classes. Not only that, these classes are being taken by some of the best educators in this competitive programming field who have been to the ICPC World Finals or have been the IOI medalists or have worked in big IT giants like Facebook, Amazon, Google, LinkedIn, etc. So what are you guys waiting for? Download the Unacademy app right now or register yourself on unacademy.com and select your goal as competitive programming to access all this free content. You may also opt to get our paid subscription, that is known as Plus subscription, after which you will be able to access the curated content by the educators, wherein you also get extra support like teaching assistants, practice problems, and live problem discussion. Additionally, don't forget to use my referral code DarshanCool25 to get an instant 10% discount on the Plus subscription. So now that we have understood the solution, let's move towards the pseudocode. The pseudocode goes as follows. For each test case, we will take the input for L and R and then form our quadratic. Then, if the roots of the quadratic exist, then we calculate the roots, that is alpha and beta, and then we initialize our answer variable to 0. Further, we add R beta minus L alpha plus 1 to our answer, where R beta is the ending point of the range containing beta elements and L alpha is the starting point of the range containing alpha elements. After that, as we have already defined a function known as range sum which calculates the sum in the ranges where x ranges from L to R, we call that function range sum from 1 to alpha minus 1 and beta plus 1 to the last element. So once we have added this in our answer, we print our answer. And in the else case, if the roots of the quadratic does not exist, it means that all the ranges are non-overlapping. So we simply print range sum from 1 to capital R minus L plus 1. Coming to the C++ implementation of the code, we take the input for t test cases and then for each test case, we take the input L and R and calculate the discriminant of the quadratic as follows. Now, we see if the roots exist, we calculate the roots in the following manner. Remember to use the function square root L instead of just SQRT because the numbers might be quite large, so there can be precision errors. So it is safe to use square root L. Now, once we have calculated the roots alpha and beta, we then calculate the values of L alpha and R beta in the following manner. So we know already the formula for Lx and Rx. It's just that we substitute x by alpha and beta in the following lines. Once we have calculated these, we add R beta minus L alpha plus 1 to our answer, and then also add range sum from 1 comma alpha plus 1, sorry, alpha minus 1, and range sum from beta plus 1 to the last element to our answer. The formula for range sum is already defined in a function over here. The formula was discussed in the solution, so you may want to refer it again. In the else case, if the roots do not exist, it means that all the ranges were non-overlapping. So we just find the range sum from all the ranges, that is from x is equals to 1 to x is equals to r minus l plus 1. And finally, we output our answer on a different line. So now that we have completed the implementation, let's submit this code on CodeChef ID and let's hope to get a quick AC. Great, so our solution works. Regarding the complexity of this code, as all the operations in the code are directly formulas based on capital L and capital R, so we can safely say that for each test case we require constant amount of time, so it can easily pass in the given time constraints.